So I'm going to start with a very high-level background for this work. And later we will make it more accurate, more formal. So the context is machine learning. And we are trying to understand the mathematics of machine learning. So we want to have a model for learning, which is a definition, and then to prove some things about it. And the standard definition of learning, the first definition of learning, is the notion of pack learning, which is a very influential definition. But the reason we started to talk about this is that in some cases, this definition is not informative enough. It misses some valuable data, valuable information in the world. And definitions, in some sense, determine the way we think. These are the words we use. So maybe choosing or having a more variety in the definitions can help us to think better as well. So this is sort of the very high level purpose of what we are trying to do here. And the topic I will focus on is about the learning rate of an algorithm, which is, as Shai said, formally a version or a variant of pack learning, but I will explain the difference between the two definitions later on. Okay, so the summary is that we want to build some model, some mathematics behind machine learning, and this is one more layer you can add to this discussion, what I'm going to explain now. So I'm going to start with an introduction to machine learning. What is the framework? So the very high level framework of machine learning, of statistical learning theory, is that we get some data and we want to have some machine, some algorithm that produces predictions for in the future. So the framework we consider here is the data we get is a sequence of n examples. Each example is a point x and its label y. So you can think about x as being an image and y as being, does the answer to the question, does the image contain a dog or not? So this is so a list of pictures and some object, does it appear in the picture or not? So this is the data we get. Now we want to take this data and make it into a useful thing. What is a useful thing in the formalism we consider? We want to take this data, this sample S, and translate it to a function, a full function on the whole universe, on all of X. And this function will tell us in future examples that we did not see what is the corresponding Y. This is our purpose. This is the meaning of this H. And the way we do this is we have some algorithm, which is just a function from this set to this set. So a learning algorithm in the framework we consider is just a function that takes a sample and maps it into a function. Okay, so this is the framework we are working with, and it is a model for what happens in real life. And there are many objectives you can try to formally state here. I will say what does pack learning mean, or the way pack learning defines it, but first I will do it in a high-level way. So the high-level goal we want to achieve is something like this. If this list of n samples, n examples are drawn independently from some distribution, we don't know the distribution, but we assume that it is drawn from some distribution, then what do we want to do? We want to find a function h that is sort of close to this distribution mu. This is what the learning algorithm should do. And the way we measure the quality of the algorithm, the quality of the output, is we see how often does h predict the value of y correctly. So this is the way we measure the quality of the output of the algorithm. Okay, and so this type of guarantee is called generalization. We want to generalize, and PAC learning is a specific way to formalize it. But before we can, I will define PAC learning, I want to add one more layer to the discussion. So when we want to learn something, when we, as humans, the context is important. So for example, if somebody asks us, what is the next element in this sequence? Then the answer is 6, at least in my mind. And the reason is I have some context in my mind. I have I call it context. And now we want to take this thing and put it into the mathematics. So there are several ways to define the relevant notion. And the way we use it, the thing we do here is the context is a class of functions, H. This is a collection of functions. And we assume the distribution mu that is labeling the input to the algorithm comes from the class H. So we assume that there is some, or the infimum of the errors of all functions of H is 0. You can think about it as a minimum. This is not very important for this talk. So we assume that the distribution that is labeling the input comes from some class of functions. So this is the way we think of the context. The context is this class of functions. And now we have a learning algorithm, we have context, and now we can define what does learning mean, what is PAC learnability. So here is one way to define it. This is not the most standard definition, but it's equivalent and there are less quantifiers. So I'm going to use this. So this is a definition of learning. So now the first step is to define what is the error of an algorithm A with context H and sample size N. So there is an algorithm, it has some context, we can forget about it for a second. And the algorithm chooses some number of samples N. Then the error is the supremum of the expected error over all distributions. Okay, so we sample n independent samples from some distribution from this context, and for each distribution we can measure the expected error, and then we take the maximum, the supremum, the hardest distribution. So this number is called the error of algorithm A with sample size n and context H. Okay, is it clear? This is a very okay. And now the way we define learnability, so we can learn things in context H if this limit is 0. This is the definition of us being able to learn in this context. So for every n, we choose the hardest distribution, and we want, as the number of samples grow to infinity, the expected error goes to 0. This is the way PAC learning is defined. Okay, so this is a standard and classical definition. And now I want to explain what we want to add to this definition, or how do we want to revisit it. So, so before I will tell you how we want to change it, this theorem is maybe the most celebrated theorem in statistical learning theory. And this theorem relates machine learning and combinatorics. So the theorem states that if we want to learn with context H, this is possible only if its VC dimension is finite and vice versa. Okay, so this is a well-known theorem. I will not define VC dimension. It was defined, I think, several times yesterday. So I'm not going to do it now. And it's also not very important for this talk. But this is the sometimes called the fundamental theorem in this context. And this is a very nice and basic theorem. And the purpose of this talk is maybe suggest a version of it which is more informative, which is more accurate. And in what sense accurate? The first step towards the new theorem, or a version of the theorem, is the idea of a learning curve. This idea appeared in a paper of Schurman's, and it's a very intuitive idea. The first idea is that when we do machine learning in real life, the error should become smaller and smaller as more examples are seen. This is a very intuitive statement. And we want to understand the way this error goes to zero, either to be able to predict it before we actually started running the algorithm. This is one thing we may want to do. Another thing we may want to do is to actually, when we run the algorithm, to estimate it throughout the execution, and this data may be informative. It can tell us, do we make progress, or did we do enough or not? We can try to use this thing to understand what is going on. And the thing that we want to, now we're going back to mathematics, we want the definition to capture this, this thing, this idea. And the way we try to do this is like this. So when you run a machine learning algorithm in the real world, the distribution mu is fixed. It is unknown, but it doesn't change as more and more samples are gathered. It is fixed, the nature determines it, and now we can increase n, increase the sample size. And what we want to understand is the way for a single distribution mu, a fixed distribution mu, the error tends to zero as more and more samples are gathered or collected, okay? So this is the rate of a specific algorithm with respect to a specific distribution. It is the expected error when n samples are collected of the learning algorithm. Okay, so this is the learning rate of a specific algorithm. And yeah, so what now we want to take this rate and put it inside the definition that corresponds to PAC learning. And the reason we want to do it is captured maybe in some schematic way in this graph. So this graph is a schematic graph. I drew it numerically, but it demonstrates a phenomenon. So the graph, the lines in the graph, each line is a specific distribution. So this distribution starts with very small error, and it tends to zero like this. This distribution starts with very high error, but it tends to zero much faster. So every distribution has its own the way it goes to 0. And the theorem, the VC dimension theorem, tells us that the upper envelope of this graph is something like 1 over n. This is what the theorem tells us, both an upper bound and a lower bound in terms of the VC dimension. But if you care about a specific distribution, this can still go to 0 exponentially fast. So there is a different order of quantifiers. Okay, so the upper envelope is interesting, but it's a very strong property. In applications, we may want to follow a specific distribution and understand what is going on for that specific distribution. And now we make the formal definition. So here is the definition. So there is a class of functions, H. This is the context of the learning problem. And there is some function R which tends to 0. So it's like 1 over n squared, e to the minus n, some function. And now we want to define what does it mean that the rate, the learning rate, is this function. Okay. So we say that the learning rate is at most R if there is some algorithm, some specific algorithm that achieves this rate R for every distribution without knowing the distribution. But for every distribution, there is a delay factor. The number of samples is delayed by this factor C. So if this constant is larger, the rate tends to 0, the error tends to 0 slower. But still it tends to 0 in the same rate R, okay? So this is the way we define rate at most R. There is a single algorithm that for every distribution, the expected error goes to 0 like R, with some delay factor that depends on the distribution. Okay, this is rate at most R. Rate at least R means that no algorithm can do better. So you can read the quantifiers, but the meaning is that no algorithm can do better than R. Okay, so, and rate exactly R means rate at most R and rate at least R. Okay, so now we have a way to define a rate. We define the rate for a specific context. H is our learning context, and we define the rate, how hard it is to learn. Okay, the rate of this class of functions. And so this is definition is motivated by everything I said so far. And I think the reason we are talking about it is that you can say something non-trivial about it. So I just want to make 2 comments to emphasize 2 specific comments. So I wrote the definition here again. And I want to emphasize that the algorithm does not know the distribution. So it's not, it's still the same as in PAC in the sense that the algorithm does not know the distribution. It operates obliviously. It does not know the distribution. This is one comment. And another comment is that we can think about this constant C as measuring the complexity of the distribution mu. The larger this constant is, the more difficult it is to learn this distribution. So it is some way to think about this constant. Okay, and now the thing I want to tell you is that with this definition, you can prove that the rates have a trichotomy. There are exactly 3 options for rates with all the definitions I stated before. So the rate can either be exponential. This goes to 0 very fast. The next option is linear. It goes to 0 like 1 over n, exactly 1 over n. And the next option that it goes to 0 as slow as you wish. It's more than every rate that tends to 0 as slow as you wish. Okay, so this is the theorem. And here there are three, below there are three things I want to recall. First, this is true only in the realizable case. The proof is just for this specific case. Second, we need the class to have more than 2 functions. I will comment it about this later. This is not very important. And third, there is some measurability assumption on this class. And I will talk about this measurability a bit later. But this is a very standard assumption. There is nothing strange in the way we define, okay? So this is the trichotomy theorem. And now I want to explain one part of this and discuss some ideas in the proof, okay? So again, there are 3 comments. First, the first comment is that the conclusion from this theorem is that the rate cannot be this function. This is a conclusion from the theorem. Such a rate is not an option. A second comment is that Schurman's, in the paper I spoke about, I mentioned before, proved a version of this, which is a dichotomy for a very specific type of context, H's, which are chains. So it's a very, very specific case of what I explained. And the third thing is that intuitively, the more complex this class of function is, the slower the rate should be, because the learning should be harder. And the way we measure the complexity of this class of functions is by its shattering capabilities, similarly to the way VC dimension is defined. Okay, so and now I want to explain a little bit about the proof. So here I'm going to explain how do you prove exponential rate? How do you analyze the exponential rate? So the claim here is that the rate is exponential if and only if this class of functions, H, does not shatter an infinite little stone tree. Okay, so this is the one part of the argument. So now I will explain we know what does it mean that the rate is exponential. Now I will explain to you what is written here. So a little stone tree is an infinite decision tree where the vertices, it's a binary tree with the root. All the vertices in the tree are labeled by elements of the set X of the universe. And every edge in this tree is labeled by either 0 or 1, like this. The right edges are labeled by 1 and the left edges are labeled by 0. And now every vertex in this tree, like this vertex, defines a path from the root to the vertex. And this path defines a partial function. This function maps x1 to 1, x3 to 0, to 0. So every node in this infinite tree defines a partial function. And we say that a class H shatters this infinite tree if for every node in this tree, there is a function that can reach it in following the tree, Okay, so this means that an H shatters an infinite tree if it can reach every single node in the tree, not the leaves. The leaves are outside the tree, just every single node inside the tree. And does not shatter means that there is no tree that H shatters, okay? So this is a combinatorial condition that characterizes exponential rate. This is the claim. Does it make sense? Okay, I can see a little bit of information from you. Okay, so to prove this claim, we need to do two things. First,
Amir, maybe you'll give an example later, but if not, can you give a good example of the class H that would satisfy this?
Okay, when H does not shatter an infinite tree, so maybe a few examples. One is H is a finite class. This is one example of a class that does not shatter an infinite tree. Another example is maybe all singletons in N. So these are sets of the form. So just all sets of a single element inside the natural numbers. This is another example of a class that does not shatter an infinite tree. Example of maybe if H, this does not shatter, doesn't. Maybe a class that does is if we look on all functions on the integers, this is a class that does shatter an infinite tree. This is all functions. So these are just extreme examples, and there are more complicated examples, but I think this is a good set of functions to consider. So these are simple classes. The rate is exponential. This is a complicated class. The rate is slow.
You have 5 minutes.
Okay. So to prove this, we need to do two things. First, to prove that if the size is more than 2, the rate is not smaller than exponential. This is very easy to prove. It's really an exercise, so I will not do it. And the other thing is to prove the more interesting thing is to say if H does not shatter an infinite tree, then there is an algorithm with exponential rate. There is a very good learning algorithm. This is what we want to prove. This is the content in the theorem. So, and this is a somewhat surprising statement. We want to start with the assumption that there is no tree. This is the information we have. What we want to deduce is that there is some learning algorithm. So this is the type of logical step we want to accomplish. And the way you typically do such steps, you start with there is no something, and you want to deduce that there is something else. And the standard mechanism for doing this is duality. So I have one slide on duality. So duality is a very powerful idea. The simplest example of duality is if there are two disjoint convex bodies, meaning that there is no point in their intersection, then there is a separating hyperplane. So there is no point implies there is something else. And a different place where duality appears is in game theory. Specifically, in our case, it's a family of infinite games called Gale-Stewart games. And in game theory, the duality comes in our setting as saying, if one player does not have a strategy, then the other player does have a strategy. So this is the side, there is no strategy for one player, then there is a strategy for the other player, okay? So this is true for a very general class of infinite games called Gale-Stewart games. I will not define this right now, but I want to point out one difficulty for us that comes from this framework. This is a very abstract framework that is sort of set theoretic. Everything is defined in a very basic language. And duality is also very abstract in this setting. So what is the problem for us? Eventually, this duality should yield a strategy. So it gives us a strategy, and this strategy should be an algorithm. We eventually want to get an algorithm. So a problem we need to solve, or something we need to understand, is why is the strategy this duality gives us not crazy? Why can we use it in the context of probability theory? Why is it measurable? Okay, so how can we take this very abstract scenario and produce something that is not crazy? So this is something that took us some time to understand. And I will, the next slide is about, I will give you one idea of how, or some idea of how did we manage to understand that this strategy is not crazy. Okay, so this is the next thing I want to talk about. So we started with, there is no tree. We got a strategy from this abstract game theory, and now we want to understand this strategy. Why is it measurable? Why is it not crazy? And a very helpful idea is this idea. So in a game, a useful thing to have is when you look at a position of a game, for example, on a chessboard, you want to ask or answer in how many steps can the white player win. This is a very informative data, right? How many steps are required to achieve win? And when the game is infinite, a way to measure this number of steps is using ordinals. Okay, so you can use an ordinal to measure how many steps are required to reach victory. In our context, it leads to a definition, an abstract definition of Littlestone dimension. So you can define Littlestone dimension relatively abstractly using ordinals. So here is a definition. I will not go over it right now. But the point is that the Littlestone dimension now is not an integer. It's an ordinal. It's an infinite integer, you can say. How is this useful? This is useful because there is a very nice theorem in set theory that tells us that when the class of functions H is measurable in a standard sense, then this Littlestone dimension is not crazy. It is countable. So this helps us to control the complexity of the strategy. Okay, so this is it. I'm done with the abstract ideas. I want to recap the picture again. We wanted to prove that if a class of function H does not shatter an infinite tree, then there is a very efficient learning algorithm with exponential rate. It learns very, very quickly. How do we do this? We assume that there is no little stone tree that is shattered. We go to a strategy from the duality of game theory. This strategy is not crazy, so we can use it to build an algorithm, and this algorithm is the learning algorithm. Okay, so this is a very high-level description. And now I want to just summarize the talk. I see 1 minute. So the starting point of the talk is to understand the way the rate tends to 0 is an valuable information. And now we want to take this valuable information inside the mathematics to understand, to build a theory that captures this information. And in the specific way we defined rate, we could prove that there are exactly 3 possible rates, either very, very fast exponential, or 1 over n, which goes to 0 but not very quickly, or something you can never bound. It goes to 0 as slow as you wish. And the way we prove this is using the shattering capabilities of this class of functions. If there is shattering, then we can use the tree to build a hard distribution. I did not explain this today. And if there is no shattering, then we can get an algorithm using duality. This is the very high-level idea in the proof. And the way we understand this algorithm is using pretty abstract ideas. So this is all I wanted to say, and I hope it was, you got a few interesting ideas from this talk, and thank you.
Okay, thank you, Amir. And we have a couple of minutes for a few questions, because we started late. So are there any questions from the audience?
When you say hard distribution, what sort of distributions do you obtain there? Are the distributions rather crazy?
And so I will try to give an example. So the distribution is something like this. So there is an infinite tree that is being shattered. This is the scenario when we get a distribution. And then we look on some path to infinity. This path defines a sequence of points in the set. x1, x10, x5. And you give each of these points some probability. So it is supported on the distribution eventually is supported on a countable set, and each point gets some positive mass in some not too complicated way. So it's not a very crazy distribution, but it's a pretty general thing.
Okay, thanks.
Are there any other questions?
I had a quick question also. So about the linear rate, is it the case when the VC dimension is finite then, but the little stone dimension is infinite?
So it is, maybe one comment, a class can have infinite little stone dimension, but still it does not shatter an infinite little stone tree. These are not the same.
Okay.
But up to this difference, then yes, the next step is having an infinite VC dimension, but in the relevant sense.
So shattering the same type of tree, but with the same labels?
So the type of the tree for the VC dimension is now every every node is labeled by many variables. And then let's say 3 variables here, and there are 8 things going out corresponding to all the labels. This is somehow, this resembles VC dimension. This is shattering. So this is the type of structure that is.
But the labels can be different on different branches.
So it's the same thing, except that every node is now, the nodes here have 1 variables, the nodes here have 2 variables, the nodes here have 3 variables, and so forth. So the size of the nodes sort of becomes larger and larger, and so also the out degree, but other than this, it's the same. Every path defines a function, shattering is shattering, and the same thing.
Okay. Thanks.
Okay, I see there is a question from Manohar Kaul. Dear Amir, how does one pick a set of realizable hypotheses? Does this depend on the learning task at hand? Sorry, have a look. Okay. Yeah, you cannot use his mic.
I'm not sure that I understand. Maybe the question is about how realistic is the realizable assumption, maybe. So if I understand this correctly, then this assumption is not directly related to what happens in the real world. The way it is typically done is there is a notion called agnostic learning, where we don't assume anything on the underlying distribution, but we compare our output to the best in some specific class of functions. This is called agnostic learning, and you can try to do all of this in this setting, which is more general. And we still did not do this, and we are planning to do this. So if I understood the question correctly, I hope I answered it.
Okay, yes, apparently you did. Okay, so yeah, maybe I just want to make one comment that on the practical side, there have been many works, including recently for neural networks and stochastic gradient descent, and for kernel machines earlier by Francis Bath and co-authors, and by Kolchinsky and Tsibakov and others, that proved exponential rates for specific popular practical learning algorithms. And they also used the notion of margin, which we mentioned yesterday. And this is on a technical level related to this notion of infinite Lilston trees or Lilston trees. For those, I mean, you don't need to know why, but it is a well-known fact. So in some sense, these results that Amir presented can be seen as an abstract manifestation of these specific results for particular algorithms. And another comment for the audience that have more background in discrete geometry is that a version of these questions for epsilon nets, let's say, or for epsilon approximations, is what happens. So what does epsilon net tells us? That if you have some distribution and you want to hit all ranges in the range space that have measured at least epsilon, then you need d over epsilon examples. But this is a worst case. So no matter what the distribution is, the number of samples you need is d over epsilon. Now imagine that you have the distribution fixed and you let epsilon go to 0. How does the complexity of the size of the epsilon net changes for a fixed distribution as epsilon goes to 0, rather than for a fixed epsilon over the worst case distribution? This is kind of the variant of this question in the world of epsilon nets, epsilon approximation.